Imagine a customer walking into a software company. They say, "I need software for my business." That sentence kicks off an entire engineering process. Jumping straight into coding causes late deliveries, high costs, poor quality, and project failure. The software crisis. Watch it change. Software engineering provides a systematic cure, replacing chaos with a strict, organized flow. Plan, develop, test, and maintain. High-quality software is the direct output of this organized process. Reliability is built through systematic engineering rather than isolated acts of coding. This six-step staircase represents the software development lifecycle, or SDLC. It provides the exact roadmap developers use to build the customer's requested software, from gathering requirements all the way to maintenance. This table compares how developers execute that roadmap. Line 1 shows the waterfall model. Notice the street directional flow. Developers only use this when the customer's requirements are entirely fixed. The next two lines show alternatives. The prototype model uses a cyclical loop for unclear customer needs, allowing them to test a sample first. Below that, the evolutionary model uses expanding concentric circles, showing how apps like WhatsApp grow in versions over time. Line 4 shows the spiral model. This quadrant graph maps a spiral line passing through planning, risk analysis, development, and evaluation. This is the mandatory choice for defense or medical software, where analyzing risk is the highest priority. Selecting the correct model prevents catastrophic project failure before a single line of code is ever written. This two-column layout is the Software Requirements Specification, or SRS document. Developers use it to lock down exactly what the customer needs. On the left, we have functional requirements, what the software does. On the right, non-functional requirements, how well it does it. A functional requirement defines a specific task or feature. A non-functional requirement dictates the performance, security, and usability metrics that feature must meet. Let's test this. Think about calculating a worker's payroll. That is a functional requirement. Now think about loading the payroll data in under 2 seconds. That is a non-functional requirement. Without separating the what from the how well, developers risk building an application that technically works but is too slow or insecure for the customer to actually use. With requirements locked, developers move to the design phase. They break the software into modules using 2 levels: high-level design for the big picture and low-level design for the granular details. This diagram shows a principle called high cohesion. Look at the large circular boundary. The thick lines connecting the interior nodes mean everything inside this single module is heavily related and focused on one specific task. Now look at the second boundary that appears next to it. They are connected by a single thin dotted line. This represents low coupling, meaning these separate modules have minimal dependencies on each other. Building modules with high internal cohesion and low external coupling ensures that when developers update one part of the software, they don't break the rest of the system. This block of pseudocode represents the coding phase. Here, programmers translate the finalized design blueprint into functional source code, typing out the exact logic to calculate a worker's salary. Once the code is written, it has to be tested. Testing is the active process of trying to break the software to find bugs. Debugging is the subsequent act of fixing those bugs. This bottom-up pyramid outlines the sequential hierarchy of testing. Developers test small unit parts at the bottom, integrate them, test the complete system in the middle, and finally get customer acceptance at the top. This side-by-side comparison shows the 2 major testing approaches. On the left, the solid box represents black box testing, where users evaluate inputs and outputs. On the right, the transparent box represents white box testing, where developers examine the internal source code. It is impossible to test everything, but applying these structured testing levels catches major flaws before the software ever reaches the end user. This timeline illustrates deployment and maintenance. Starting from the initial release node, it branches outward to bug fixes, new features, and security patches, showing exactly why software development never truly ends. This expanding web connects everything we've covered. It links the SDLC roadmap, the 4 models, the SRS document, design principles, coding, testing, and maintenance into one complete architectural blueprint of Unit 1. Here is your exam checklist. Memorize the 10 golden formulas. For long answers, always include a precise definition, a neat diagram, clear advantages, and real-world applications. These stages map out the conceptual framework for Unit 1, but having a process on paper is different from executing it in the real world. A new problem remains. Who manages the developers? How do we calculate the budget? And what happens if the schedule slips? These questions bring us to Unit 2, Software Project Management.